Moving right along, the follow-up to work is a concept of energy. Historically, like this caloric, the word calorie comes from something called caloric. They had messed up ideas about heat energy way, way, way back. So literally, it took decades for physics people in the way back to figure out how heat and friction and energy, how they all fit in together. So I wouldn't say new, but it's relatively new, thermodynamics and how people figured out the concept of energy. Again, energy is one of those words that if you've been alive, as long as you've been alive, you know what energy is. You've put together a framework in your brain of energy. We just got to make sure that the framework in your brain matches the actual physics of it. The definition of energy, if you were to Google it, you might find, or ChatGPT it, whatever you crazy kids use these days, you'll find all sorts of stuff. But basically, if we can boil it down, if something has energy, that means it has the ability to do work. When I teach high school kids, this is what they remember from like their grade 4 and their grade 5 science teachers in elementary school. Energy is the ability to do work. A simple definition, but what I don't like is what kind of came up before. To really get energy, you really kind of got to understand work. Um, if we don't know what work is, then saying energy is the ability to do work, that's not very helpful. Work was this weird thing about pushing and making move. So really what energy is the ability to put a force on something and make that something move. Another way to think about work and energy is they're basically synonyms of each other. I'm going to make up questions, we'll do some together, and the question might say, how much work was done to blah, blah, blah. It might say how much work was done, but we're going to use an energy equation because if you do work on something, then that something's gained energy. Some old folks in thermodynamics called this the work energy theorem. But if you do work on an object, that object gains energy. Let's say we're taking a little social break and you do 100 joules of work pushing a bowling ball. If you do 100 joules of work pushing a bowling ball, then the bowling ball would have gained 100 joules of energy. If we were really clever, maybe you could have that rolling bowling ball crash into something. And in theory, since that bowling ball has 100 joules of energy, the bowling ball can now do the work. So maybe we have the bowling ball bump into something. The bowling ball could do 100 joules of work on the something it bumped into. We're going to talk about this more, but what's cool or interesting or weird about energy is that it can kind of slosh around from form to form and from object to object. I get up in the morning, I have a healthy breakfast. That's where I get my energy from. We can't make energy. So I got to eat some food to get my energy. And then for some reason, I grab this bowling ball and I do 100 joules of work on the bowling ball. Since I did work on the bowling ball, I would have 100 joules less energy. The 100 joules would have got transferred into the bowling ball. Now the bowling ball's got 100 joules of energy. And if we're clever and we have the bowling ball bump into something, then whatever the bowling ball bumped into, that new thing gets 100 joules of energy. If this didn't start with me, but start off with like a little robot or something, a battery powered thing, we'd have to charge the batteries up. And after this robot thing shoved the bowling ball, the battery pack would have 100 joules less energy in it. And if it just threw bowling balls all day long, every time it threw a bowling ball, its energy would go down by 100 joules, constantly losing energy as something else gains the energy. So that's what's weird about energy, what took people a while to figure out. It kind of sloshes around from object to object and form to form. There are lots of different kinds of energy. If we were together, I would get you guys to brainstorm and come up with a bunch of them. I'll doodle some down, but before I start writing, this is something you've heard of. This is words you've used. Can you think of two or three kinds of energy? I'm going to kind of work backwards. The three that we're going to focus on today are gravitational potential energy, we're going to focus on kinetic energy. And the third one we're going to focus on is heat energy. There are lots of others. There is electric energy. There is solar energy. There is chemical potential energy. There is nuclear energy. You could probably come up with more, but there's many, many forms of energy. What they have in common is that same idea. Their metric unit would be joules, and they have the ability to do work, the ability to push something around, to get some sort of job done. Okay, the three we're going to focus on in order. Gravitational potential energy. If you lift something, and just let's kind of think about the mechanics. If you're lifting something, you got to put a force on it and you make it move. So that's the definition of work. That's the definition, the connection to energy. You've put a force on it and you've made it move. When you've lifted it up high, it has more energy than it did before. Let's go back to that bowling ball idea. Let's say you had a bowling ball and you're just holding it a little bit above the ground. If you were to drop the bowling ball and it landed on something, maybe a clever engineering type person, the bowling ball lands on something. If you drop it from a little distance, it could do a little bit of work on whatever it landed on. If you drop it from a higher distance, because it's falling for longer, maybe it's going faster, it could do more work on whatever it landed on. So that's kind of the logic. When things are higher, they have more energy, but then when they're lower, we call it a potential energy because it depends on if it landed on the thing. It could do work. It's kind of a stored energy, we like to say. There is a cool little proof, but for the interest of time and the way this course is laid out, we don't have to go over the proof. We have an equation for gravitational potential energy. Gravitational potential energy depends on the mass of the object. Depends on the mass of the object. It's all about gravity, so it depends on the gravity strength. The moon, weaker gravity, there'd be less gravitational energy on the moon, and gravitational potential energy depends on the height. When we put that out of words and into symbols, our short form for mass is letter M. Gravity strength, we've seen this one before, that's that lowercase g. When we're on Earth, G is 9.8, or sometimes people use 9.81, but I'll usually use 9.8. And the short form for height is H. That's our equation for gravitational energy. It'll be on your equation sheet. We just have to be okay at kind of crunching that one out. All right, classic. We're not on the second floor for our class, but there's some classes up on the third floor. Let's say you started off on the ground floor and you had to walk up 2 flights of stairs. Roughly speaking, I've measured it in the past. If you're climbing up to the third floor, that's roughly a height of 8.5 meters. Let's say we have a 75 kilogram person doing that. We can figure out how much work the person did. The question is asking for work, but we're not going to go back to work equals FD cos theta. Because there's a change in height, that's going to trigger our physics brains to use EG. So even though it says work, I'm not going to grab that FD cos X equation. Because a person's changing height, I'm going to grab the EG equals MGH. 75 times 9.8 times 8.5. I practiced this. When I did it, I got 6247.5. If we're going to be a little bit nitpicky, I'm not going to be too nitpicky, but I'm not sure what other classes require. Just going to try and do a better job of it. We should round this to 2 digits, which means 6200. Oops, and I goofed. This one's in joules, not meters. So you're on the ground floor, 75 kilograms. You carry it up to the third floor. The work done to do that is 6,200. If we round it off, 6247.5 joules of energy. If this was a little robot climbing up and down stairs, every time the 75 kilogram robot goes up these 8.5 meters of stairs, they would be doing 6247 joules of work, like their battery pack would go down by 6247.5. The flip-flop is once you're at that 8.5 meter height, if you had a big 75 kilogram thing and you kind of let it fall and maybe landed on a big teeter-totter or something, a big spring, I don't know, engineers came up with something clever. If the 75 kilogram thing goes down the 8.5 meters, whatever it lands on, it's going to give those 6247.5 joules to whatever it lands on. So it's an energy that's stored in it. In theory, we could harness the energy if we could allow this thing to fall and do work on whatever it landed on. I don't want these video clips to get too long, so I'm going to pause this one and then we'll come back with kinetic energy.